So good morning students. We'll continue with unit number 3 and this is our last topic number 7, which is earned value in a project, EV, resource, aggregation, allocation, smoothening and leveling. The first topic is earned value in a project. This is in continuation with our previous class. EVA is a method that allows the project manager to measure the amount of work actually performed on a project beyond the basic review of cost and schedule reports. So EVA provides a method that permits the project to be measured by progress achieved. So the project manager is then able to use this progress measure to forecast the project's total cost and date of completion based on trend analysis or application of the project's burn rate. So this method relies on a key measure known as the project's earned value. To report the accomplishments of the project, we must apply earned value, that is EV, to the figures and calculations in the project that is assigned to us. So EV is the quantification, that is you have to quantify of the worth of the work done to date. So in other words, EV tells you in physical terms what the project has accomplished. As with PV and AC, EV can be presented in cumulative and current fashion. Cumulative EV is the sum of the budget for the activities accomplished to date. So current EV is the sum of the budget for the activities accomplished in a given time period. Earned value is also called budgeted cost of work performed, that is BCWP. Planned value PV is determined by the cost and schedule baseline. Actual cost, which is AC, is determined by the actual cost incurred on the project. Earned value tells you, EV tells you in physical terms what the project has accomplished so far. Next, resource allocation, that is loading. After each activity has been assigned its resources, the next step is to aggregate the resources used by all the activities. So resource aggregation is simply the summation on a period by period basis of the resources required to complete all activities based on the resource allocation carried out previously. So the results are always shown graphically as a histogram. Such aggregation may be done on an hourly, daily, or weekly basis depending on the time unit used to allocate the resources. So when a bar chart is used, the resource aggregation is fairly simple and straightforward. For a given bar chart, resource aggregation chart can be drawn underneath the bar chart. However, a separate graph will be required for each resource type. As I say this, you just look at the figure. So an example is shown in figure 6.2, where for a particular resource, the required resource units for each time period are written on the bar chart. The total number of resource units for each time period can then be summed, that is added or aggregated, and a source aggregation or load chart can be produced as presented underneath the bar chart. Thus, having a project scheduling is necessary to facilitate the bar chart drawing. The non-critical activities, activities which are not on the critical path, which do not have fixed starting and finishing times but are constrained by the earliest and latest starting and finishing times. So this situation offers the planner chance for adjusting the demand for resources. This figure you can see the resource aggregation chart showing the requirements associated with earliest start time and latest time, along with the highlighted resource requirements, that is the resources that will be needed for critical activities. So figure 6.3 illustrates such situation, as I have mentioned earlier, which shows the resource aggregation when the activity is scheduled or planned on the early times and late times. So it can be seen that the resource requirements that arise when both earliest and latest start times are considered are different. So the shaded area represents the resources required by the critical activities, as these activities have a fixed position because the early times equals to their late time. Figure 6.3 shows also the accumulation of resources at the beginning of the project when the activity is scheduled on the early time. So on the other hand, the resources accumulate at the end of the project when the activities are scheduled or planned on their late times. Resource allocation. Resource allocation is also called resource loading, is concerned with assigning the required number of resources identified for each activity in the plan. More than one type of resource may be assigned to a specific activity. For example, fixing steel plates on a bridge deck may require different types of resources such as welders, laborers, and a certain type of welding machine. From a practical view, resource allocation does not have to follow a constant pattern. Some activities may initially require fewer resources but may require more of the same resources during the later stages of the project. Resource smoothening. Shown in the figure, the problem of resource fluctuation appears after the initial scheduling or starting of the project without considering the resources. The peaks and valleys in the resource profile indicate high day-to-day variation in the resource demand, and resource smoothing is the process that attempts to determine a resource requirement that is smooth and where peaks and valleys are eliminated. For example, even if 7 units of a given resource are available at any one time, utilizing 5 of these units each week is preferable than using 4 units for the first week. So 7 the next, 2 the next, and so on. So even if there is no limit to the amount of any resource available, it is still desirable the resource usage is as smooth as possible, given that the resource requirements of those activities on the critical path are fixed. So some order or priority needs to be established for selecting which activity and which particular resource associated with this activity should be given priority in the smoothing process. So this is the graph for preferred resource usage, pairing the resource units, and these are the times, 7 days to 19 days. Initially at 4.5 at 5 units it can be started and ended at 2 units. It increases gradually and it decreases the resource units. As the time increases, the resource units decreases. Next one, resource leveling. Project is classified as time constraint in situations where the project completion time cannot be delayed even if additional resources are required. However, the additional resource usage should be more than what is absolutely necessary. So accordingly, the primary focus for purposes of scheduling or planning in time-constrained projects is to improve resource utilization. That is how the resources are used. So this process is called resource leveling or smoothing. It applies when it is desired to reduce the hiring and firing of resources and to smooth the fluctuation in the daily demand of a resource. So in this case, resources are not limited and project duration is not allowed to be delayed. The objective in this case is to shift non-critical activities of the original schedule or plan within their float times so that a better resource profile is achieved. Resource leveling heuristics shift non-critical activities within their float time so as to move resources from the peak periods, high usage, to the valley periods, low usage, without delaying the project. Usually, the project managers may prefer having a desired research profile in which the resource usage starts with low values and then the resources are built up till its maximum values and starts to decrease as the project approaches its end, as shown in figure 6.4, which I have shown earlier. So you can give your reference in the chat box. Thank you.
is what we on principles of construction management. And in the last couple of lectures, we've been talking about planning and scheduling in construction projects. Today, we will concentrate on what is called resource leveling and allocation. Now, construction schedules, as we know, are either time-oriented or they can be resource-oriented. In our discussion so far, we have mostly talked about concepts related to time-oriented scheduling. Today, of course, as I mentioned, we will talk about resource allocation, resource leveling, and those concepts which are resource-oriented scheduling concepts. Now, what is resource scheduling? Estimation of activity times and project durations using network diagrams, assuming that there is no cap or there is no constraint on the availability of resources. That is what we have been doing. If you will recall, there was an earlier example, we are probably going to do it again today, that we estimate the quantum of work, have a number for the productivity of the labor or equipment, and try to come up with the time that is required to complete that activity. So we almost assume that there is no constraint on the availability of the resources as such. But in real life projects, there are resource constraints such as shortage, delayed delivery, competing demands. It may happen that you may have a set of resources, but there are different activities in the project which demand the use of that resource. You may have only 10 laborers or 10 workers, and there may be 5 activities which demand labor or demand workers to complete them. We have to decide as construction managers which activities would take precedence over the others, and so on. So there are various situations because of which we need to do resource allocation. We have to decide or prioritize which activities will be taken up first, which may be postponed to a later time. Resource planning and allocation plays an important role in managing construction projects. Now let's look at the principles involved in deploying resources to activities in a project and the resulting implications through a very simple illustrative example. We have talked of this project before when we considered a simple project having just activities A, B, C, and D with precedences as given. A and B are independent and can be started right at the word go. C depends on A and B depends on B. This is the mandate requirement as far as each of these activities is concerned. Now, we also said that A and C require labor of similar expertise, let's say T1, and B and D require labor of another expertise, which is T2. What we tried to talk about was that if we allocate, let's say, 10 numbers of T1 expertise labor and 10 numbers of T2 expertise labor, how will the project planning be done? Now, once we assume that there are 10 workers with T1 expertise available to us, 10 workers of T2 expertise available to us, we can find out that the time required to complete this project is 50 days for activity A, 20 days for activity B, 30 days for C, and 20 days for B. This is nothing but this number here, which is man days, divided by the number of laborers. Now, what this assumes is that the labor supply or the availability of labor, whether it is T1 or T2, is constant over the entire duration of the project. Representing this project on an activities and arrow network, we can find out that if A is done in 50 days, C is done in 30 days, B is done in 20 and 20, the earliest that the project can be completed is 80 days, because this path is now the critical path. This can be done in 40 days. In this representation, what we have assumed is that as far as the labor with T1 expertise is concerned, as far as the labor with T2 expertise is concerned, both of them are employed to the fullest extent right from the word go till the project is completed. So 10 numbers of workers with T1 expertise work from day 1 to day 80 when the project is completed. Initially, for some time, they work on activity A, and then they work on activity C. In this case, we have assumed that the activity B starts at the earliest that it can, and these people who have an expertise in T2 work initially on B and then on D, and then everybody goes home. This part, of course, can actually be completed, not necessarily starting with 0, but anywhere in this region, provided it is not going beyond the 80-day limit when A and C will get completed. Now, this approach, which assumes a constant deployment of labor, has its own problems. Uniform availability of resources is perhaps neither possible nor desirable. Moreover, it's not advisable as well. Few obvious reasons could be mobilizing sufficient funds during the initial stages of the project may not be possible in most projects. Most of the construction activities happen during the middle stages of the project, and hence it is recommended to have a gradual increase in the deployment of resources in the initial stages and gradually decrease it after meeting the peak demand, which essentially happens during the middle of the project. We have talked about the S curve and its relevance as far as project progress is concerned. There are lots of reasons why most projects follow this S curve. In the initial part, it's not only the mobilization of funds, but it's also the learning experience, availability of front. All these kind of issues make it very difficult to achieve progress which can be sustained all the time. But having done that initial experience of learning, it is much easier to gradually increase the resources, reach a peak level, and then taper it off. Similarly, towards the end of the project, it's very difficult to have the entire workforce working at that project. There will be smaller and smaller areas which will be available. There will be smaller and smaller amounts of work which will be left, and therefore it makes no sense. It will be very difficult for a uniform progress to be maintained. What I'm essentially saying is, if we differentiate this total progress with respect to time, what we'll get is a progress curve. So this is our rate at which the project moves. And if the project moves gradually in the beginning, reaches a peak at the middle stages of the project, and then goes to 0 once again, what we will get as the cumulative progress is what is given in blue. Now, this is precisely the kind of deployment of labor that we would like to actually see, rather than the constant deployment as we have seen in the previous slide. What this slide shows is an alternative way of having employed the labor for completing the 500 or 300 man days of work. It really shows the deployment at different points in time, and the rest of it, I'm sure you can figure out. Now, coming to our main discussion today, which is resource planning and scheduling. There are two aspects to our discussion. One is resource leveling, and the other is resource allocation. Leveling deals with distribution of resources within the fixed project duration, and allocation deals with availability of resources under a constraint. So coming to the first part, which is resource leveling, that is the process of allocating resources among various activities such that the peak requirement of resources is reduced with a constraint on time, and the underlying assumptions in resource leveling are only one type of resource is considered throughout the project, and activities already underway should be completed first. What I would like you to recall is that activities are of two types, let's say. Critical activities and non-critical activities. Critical activities are those which must follow one after another without any gap. Without any gap means there's no float. And at the completion of these critical activities, the project is completed. So basically, the last activity to be completed has to be a critical activity. That is by definition. Now, along with the critical activities, there is a set of non-critical activities with whatever dependencies they may have. Critical activities also have their dependence on non-critical activities, but there is some float, there is some leeway, independence in deciding when a non-critical activity is done. So the whole idea of resource leveling is to make sure that the resources that are used in non-critical activities are not spread out over the project sporadically. It should not happen that over a period of time, I need a resource here, then I need it here, then I need it here. If possible, I would like to bring these resources such that they are used here and here so that this particular resource can be brought to site only for this duration and be let go. Provided, of course, that this is for non-critical activities. In the case of critical activities, there's something which we may not be able to help much. So with this background in mind, let's move forward and try to understand the steps involved in the resource leveling process. Identification of critical activities, arrangement of activities on the time axis based on their early start dates, determining the total number of resources required on each day by adding the resource requirements of individual activities planned for that day, and the resource profile determined as a chart called the resource aggregation or resource loading chart. As we do a simple example, these things will become clear. Repeat steps 2 and 3 with the activities being plotted using their latest start dates, comparing the two resource charts, that is that determined in step 3 and 4, and finding out an acceptable resource profile between the two extremes, eliminating the peaks and valleys in the resource distribution. This is done by arranging the non-critical activities within their float, which obviously means that the duration of the project is not compromised. Let's go through a simple example to understand this concept. Let me once again reiterate that what these steps essentially have told us is that a non-critical activity can start and finish as is shown here. If this is my earliest starting date for that particular activity, this is the duration of that activity, this becomes my earliest finishing time for this activity. However, without compromising the duration of the project, this activity can also be scheduled in this time frame where the duration of the project remains the same, and this is my last starting date or the latest starting date. This becomes my latest finishing date. This we get from the backward pass, and this is what we get from the forward pass. And remember that the activity can be scheduled anywhere between these two extremes, that is within EST and LST. If the activity starts anywhere in this region, it will get completed anywhere in this region, and this will not compromise the length of the project. So that is precisely the kind of thought process that goes on in leveling of resources. So let's understand this a little bit better through this example, which gives us the 7 activities as shown, their dependencies, and I've already drawn the network for you. So this here is the durations of all these activities. A requires 13, B requires 5, C requires 5, D requires 12, E requires 2, and F requires 5, let's say, days to complete, G requires 10. And this number here in the bracket is the resources. So in this case, as a simple example, we are saying that this number here represents the number of workers which is required to complete this activity. We must remember that as far as this example is concerned, we are also going to assume that A requires 2 workers, means it requires a team of 2 workers. It cannot be done or it cannot be started unless there are 2 people available. Further, it cannot be accelerated by putting more people on the activity. So with this understanding and assumptions, let's try to find out what can we do with the resource allocation algorithm which we have just learned. So the earliest and latest occurrences of the events are shown in the nodes, and they have been obtained by the forward pass and the backward pass. I'm sure you know how to do it. A can start at 0, and therefore this node here, which is node 2, the earliest it can be reached is 13. This node 5 can be reached earliest depending upon the maximum of these 3 nodes which are converging on this, and so on. So we find out that activities A, B, and G are critical, and the project duration is 35 days. So this is the first step. We find that A, B, and G are critical activities. They are highlighted by a firm arrow, and we find that the project can be completed in 35 days. Now let's try to do the next step, which is scheduling these activities on the time axis. This representation schedules these activities in the earliest start times. So A obviously starts here, finishes at 13. B, which follows this, is completed here. G is completed here, and this is 35 days. As far as B is concerned, you will recall from the diagram that it depends on A and therefore can be started as soon as A is completed. And the same thing is valid for activity C. So these activities start here on, let's say, 13 and are completed at whatever times depending on their durations, and we reach these points as is shown here. Now, on this, if we now superimpose what is the kind of resources that we need on each day, we find that as far as this point is concerned, that is, as far as the first 13 days are concerned, only activity A can be done. No other activity can be done, which means that A, which needs a team of 2 persons, is the only activity going on as far as this project is concerned, and our deployment is only 2 workers. Now, coming to day 14, we have the possibility of activity D, B, and C being carried out. D requires 2, B requires 3, and C requires 4 workers, and therefore the deployment required as far as day 14 is concerned is 9. This continues till such time as activity C is finished. Once C finishes, we have activity F which may start, and so on. What we need to do is to find out on a given day what are the activities that are going on and find out what is the demand for the labor on that particular day. So we find that beyond this point, only activity G is going on, and that requires 4 people, and that's what we have. So towards the end of the project, we have only 4 people working on activity G right up to the end of the project. This is a scenario for starting all the activities on their earliest starting times. Now, if we represent this labor deployment on the time axis, this is what we get. So we have 2 people here, increases to 9 here, goes to 8, 5, drops to 2, and then goes back to 4. What we have to see is whether this is the most desirable form of labor deployment or not. In order to be able to do that, let's try something else. Let's try to schedule the activities so that they start at their latest starting times. What we are trying to do is to ensure that G, which is the last activity, and depends on the completion of activity E and completion of activity F, is not delayed, because this is my critical path. In order for this to happen, we must make sure that activity B starts here, activity E starts here, C starts here, and F starts here, and that is precisely what is their latest starting times. So now with this algorithm, with this thought process, let's try to then find out what is our labor deployment. This is what the numbers you will get. From here to here, it will be all 2s, then it goes to 6, 9, 8, and goes back to 4. Representing this on the time axis in a manner that we did the last time as well, we find that we have possibly a slightly better situation. We have 2, 6, 9, 8, and 4. Now the point is, can we do something better than that? Now let's do yet another iteration with the same example. So let's try to do another iteration and try to see if we can remove the peaks further and reschedule our non-critical activities. But what we must remember is that we must remain within the floats of these activities. Now, with this thought in mind, that we use the floats and try to reschedule the activities, let's do this iteration. In this one, what we are saying is that activities C and F, which is here, are starting at their earliest starting times, which is somewhere here, and B and E are starting at their latest starting times. And with this, if we do the resource aggregation, we find the numbers to be given as they are at the bottom. This is the graphical representation of the resource profile that we get when we have chosen to start one set at the earliest starting times and one set at their latest starting times. Now, before we compare these 3 resource curves, I must point out that here we find that the peak demand of resources has reduced from 9 to 8. Now, this picture here shows the comparison that we have. This was when the activities started on their earliest starting times. This is what we have when we have the activities starting at their latest starting times. And this is what we have when we did the combination of EST and the LST for the different activities. Personally, to me, this seems to be the best alternative that we have so far. We can try another. You can work out more examples or more combinations with B, E, and CF separated. What we have done is B and E have been taken to both start at the same time. B and E have followed each other. C and F have followed each other as soon as the previous one was completed. So as soon as B was completed, E was